Okay, yeah, thank you. Yeah, you already know me. I'm Patrick. Yeah, I'm talking about software architectures and testing concepts now. If you have any questions, you always feel free to just interrupt me. Okay, so these are the course contents. We already have seen vehicle models, and control and optimization and network will come in the next days. Now we're in the part that is listed here last, software architectures and testing concepts. So this course is like about networked decision making, and this lecture, this talk is trying to answer the question like how to evaluate networked decision making and networked algorithms. And yeah, we create this architecture to structure the elements in an evaluation framework. And yeah, we use this to pinpoint the areas of the corresponding lectures. You've seen it in the morning already. Yeah, and it helps us to also see yeah, where to put these modules in the evaluation framework. Now, I want to think about how can we reflect these modules really in the evaluation framework. And yeah, this time I'm just talking about all of the components here because all of them all together make up like the framework, which is the CPM Lab. So I will come back to this slide once in a while. Yeah, this presentation is mostly based on Bassam's thesis. It's on networked model predictive control, but I'm also like giving a glimpse into extreme programming, which is the software development paradigm, you could say, and yeah, just a reference for good coding practices for easy maintenance and stuff like that. The gang of four is here. Yeah, we have several publications on the lab. If you are interested, you can read more about the Cyber Physical Mobility Lab there. So the first one is it's a general overview over the complete platform of the complete Cyber Physical Mobility Lab with all its components and yeah, how you can run experiments in it. The second one is about the vehicles that we use in the lab. And the third one focuses on the indoor positioning system we developed to use. I will talk more about the contents also during this talk. Yeah, but let's start with the motivation. So I want to ask the question, what possibilities we have to evaluate networked algorithms? And yeah, it's perfect that we, many of us work in this area. So now I can use you as an example. So for example, we could have Maximilian, and for the sake of argument, have him develop an algorithm for flying taxis, or Josef or Berthard for submarines. And then yeah, you want to test these algorithms, and you go up to your professor and say, hey, I have developed this great algorithm. Yeah, I just need 20 submarines or 20 flying taxis and several square kilometers to test this. Just give me the money and yeah, it'll be perfect. And chances are, yeah, you won't, or they won't give you the money. So yeah, sadly, you go back to your PC and you run the whole, your great algorithm in simulation, and everything works great. And you create perfect results. You write a paper about it, and then you submit it. And then the reviewers say, yeah, but you only evaluated in simulation. What are the effects of the real system? Can you prove that the algorithm works in the real system? And yeah, of course, this all leads to this kind of middle ground where you use a scaled version of your real system, so that you have certain elements of the real system that you can still you still evaluate with these like real kind of components to your experiment. And but it's still easy to use. If you can do quick experiments, it's not so expensive, and you can do rapid changes. You don't need to organize all of your this complicated real system. So, for example, you could work with drones or under 25 kilogram flying vehicles as well. Here we work with ground vehicles, as Bassam already said. And here's an abstract illustration of the Cyber Physical Mobility Lab. And I will talk about the components more later. But here, just to give you an impression, I will, again, for this explanation, stick to this sense, plan, act paradigm. So in the sense category, we have the positioning system, which consists of a camera which is mounted above the vehicle, the track, and the camera is connected to a computer, which does the like basic image processing, and then this computer knows the poses of the vehicles and can send these poses with this router to the vehicles and to the high-level controllers. And the high-level controllers are in the plan category. So these are responsible for planning trajectory, usually in our case. This is kind of a specialty in our lab. We have these high-level controllers, or usually you would have a high-level controller mounted on your platform. So, for example, if you have an autonomous car, you have a large computer in the trunk or something like that. But since we are working with such small cars, in a scale of 1 to 18, we decided to have the high-level like processing power separate from the actual vehicle. So yeah, we have one computer for each vehicle, and these high-level controllers then plan for their assigned vehicle and send the plans again to the vehicles. On these we have also, again, we have this hierarchical structure, but I will talk more about it later. And the vehicles just use these commands and execute them, so they are the act part of this paradigm. And yeah, since we cannot go into the lab, but I just want to give you an idea of how the room looks like. So you have to use your imagination for a bit. So you would come in through the door, and then you have a large window front in front of you, and there are we have 6 tables with chairs, so you could sit on these tables. Imagine you would sit there if you work on the lab. And then we have the interpositioning camera, which is mounted straight above the driving area, and the driving area is 4 by 4.5 meters. And as Bassam already mentioned, hopefully we will run your implementations in the lab, do the real experiments, and then we have mounted a camera here, so you will see the experiment from there. Okay, so I talked about how these components in the lab communicate with each other, and some do this communication locally. For example, if you just use sensor data in the vehicle to the mid-level controller, but some are communicating through the network. For example, the interpositioning system talks to the vehicles and the high-level controller over network. And we need some sort of framework to do this communication. And we use the data distribution service. It has a publisher-subscriber concept. So I have created a simplified illustration here. You can imagine that there are publishers who write data and subscribers who read data. So yeah, you see the participants in the network here. You also can imagine as services of the complete system, and they communicate with each other. So a publisher writes to a topic. When a topic is just like a channel and where you send data in specified formats and specified message formats. And a subscriber can then subscribe to a topic and reads all the data that is sent. And there are, you can have multiple publishers publishing to the same topic, and also multiple subscribers subscribing to the same topic. And what this, the benefits of this are manifold. For example, you have easy interoperability between different operating systems, or between different programming languages. So the only thing you need is to have access to this, to have an interface to this data distribution service. And then as long as you can read or write to or from topics, then you can take part in the system. And yeah, another benefit is that you have the interfaces between the components or participants defined, because you need to define this message format which you exchange data. That makes it easy to switch out participants or services. And I want to specify this on the example of the CPM Lab. Again, the simplified representation. In the lab, we have several topics. I wrote down 3 of them here. For example, we have the pose that is generated from the in-air positioning system, which measures where are the vehicles right now. And we have the state, which also encompasses the vehicle pose, as it is estimated from the vehicles themselves, but there are other information as the vehicle speed or acceleration from the data from the IMU. And then from the other side, we have the commands that are sent from the high-level controllers to the vehicles. And in the middle, so I'm going to the participants now. In the middle between high-level controllers and vehicles, we have a middleware, which just serves as interface between the vehicles and the high-level controllers. And this might not seem so natural at the moment. Why not just send the data directly? But I'll come back to this later. Just an example for how such an IDL file might look like. You just define basically the data you would send. So, for example, if you were to send a pose, then you would have an integer which specifies the vehicle's ID, and you would have doubles or something like that for your position in X and Y direction and your orientation. The same works for the trajectory. So additionally, you would have an ID, and then you would have trajectory points, for example, specified as positions and speeds or velocities. I continue to the indoor positioning system. So now we're in the sense area of this architecture, and our perception is made up of 2 parts: one, the indoor positioning system, and 2, the sensors on the vehicles themselves. So as I mentioned before, the camera in the positioning system is mounted above this driving area and yeah, streams images with 50 Hertz. So we have a new image every 20 milliseconds. And the, yeah, or maybe you know about in-the positioning systems. There are several approaches to this. So some work passively. So you just have a camera, and for example, you have a QR. Hopla. You have a AR tag on the like the component you want to see, or you have a specific arrangement of I don't know, balls or something you can detect. And this is more like here the vehicle that needs to be detected, it has this active yeah, it has an active part. So we have 4 LEDs that are flashing on the vehicles. So 3 are just they are always on, these pose LEDs, and they form this non-equilateral triangle. So you can also see the orientation of the vehicle if you see the 3 outer LEDs. And then you have 1 LED in the middle, which has a certain frequency, which just encodes can imagine like a Morse code, its ID. Yeah, but the camera just has really low exposure time. So what the images that come out of it are almost black and white. You just see, so this is not much of a simplification. It's really like the floor is really dark, and then these active LEDs are really bright. So you have just dots wherever the vehicles are. And then if you, the pipeline to go from this image to the actual poses, it's just we extract these LED points, and then we make this transformation between image coordinates to world coordinates, and then try to find the vehicles in there. I mean, you can probably see with your own eyes at the moment that there are 3 vehicles, and yeah, there's just some basic like we try to find match the points to vehicles. So this is just like, I don't know how to say in English, but yeah, it's kind of like logic. It's not hard to do. You can imagine how to do it, and yeah, then we can extract the position orientation and the ID from the vehicles. If you see a stream of images, and then you compare or you track the single vehicles, and then you can also track the vehicle ID LED, and you can then see the sequence of on-off signals it gives, and from there you can see the ID. Okay, yeah, the interface of the IPS is just from the camera, it gets the image. This is not done with DDS, but yeah, locally on the computer. And yeah, it sends the pose via DDS to the high-level controller and the vehicle. And yeah, let's look at the vehicle and see how it uses this pose. Yeah, again, as I mentioned before, the vehicle also has sensors on it, and the vehicle does the act part also, so it controls the actuators it has. We created our model scale vehicles based on a mechanical platform that is readily available. So it's an off-the-shelf platform of a model scale race car. It's called X-Ray M18 Pro. Yeah, people use it also to drive, to compete in races. But yeah, we we just took the mechanical base of that and then we modified it in order to work for our networked experiments. So we added sensors, actuators, and computation units. For sensors, we have inertial measurement unit, which measures acceleration and accelerations and yaw rates, or how do you say it? Rotation rates? I don't know. Yeah, and we created a custom.
And Patrick, if you finish your or stop the presentation, you can go to Bildschirmpräsentation and Anzeigedauer verwenden, deactivate. It was now a mix between English.
I'll try.
Bildschirmpräsentation. In der Mitte Anzeigedauer verwenden, wegmachen. Genau.
Okay.
Now, because the slides were switching.
Yeah, it threw me off a couple of times. Okay, thanks. Yeah, where was I? Yeah, we have this custom odometer, which measures the speed and the travel distance. And yeah, we used Hall effect sensors, and which are sensors that measure magnetic fields, and yeah, a magnet that is mounted on the motor shaft. I will show that in more detail. Yeah, and then we have, for actuators, we have mainly like steering and propulsion. So yeah, for steering, this is a servo motor, and for propulsion, a DC motor. And then for computation hardware, we have two boards on there. So a Raspberry Pi Zero, which you use for wireless LAN and synchronization of clocks in the lab. And it also does the sensor fusion job, and yeah, computes control actions to follow trajectories or to follow a path. And the low-level controller, which is an Atmega, it's our hardware interface. So it reads the sensor data and it yeah, sends the commands for actuation of the actuators. Yeah, so we have a short animation of how this vehicle is constructed. So you see the base elements of the platform, like how you would buy it in the store here. Yeah, it has the servo motor and a battery, and then we added, I don't know, it's kind of not running smoothly at the moment, this animation, but here you see that we added a printed circuit board on top of it with the Atmega, and to this PCB we connected the Raspberry Pi, the IMU, and a motor driver, which is used to actuate a brushless DC motor. On top of that, we have the LEDs, which are used for positioning. Yeah, again, the outer ones for the pose and the inner one for the ID. And yeah, you see on the back here we have another smaller board, and its purpose is just to control the LEDs, and it also holds these 3 Hall effect sensors. And you see this magnet now, which is attached to the motor shaft. When it rotates, it changes the magnetic field in these Hall effect sensors, and through this we know the rotation speed of the motor. Yeah, we have different operating modes for these vehicles. You can just control them directly from your high-level controller. If you just give commands for your motor and steering, but there are also more abstract control modes. For example, you can set a certain speed and a curvature, and the vehicle tries to follow that. Or you can set a certain speed and a path, or even a trajectory. And I will present two of them more closely. The path tracking, where we just implemented this a Stanley controller, which is a very simple path tracker, but it works decently well. I mean, it was used in the, if you know, the DARPA autonomous race car challenge. I'm not even sure if it's race car, but they drive through a desert, and it kind of boosted the development of autonomous cars. And the vehicle that won the DARPA in 2005, they used this controller to track the path. Yeah, for trajectory following, we have a model predictive controller implemented on the Raspberry Pi, and yeah, it uses a simplified bicycle model to predict the states. It uses the servo motor values as an input, this model, and the battery voltage, and outputs the pose, the steering angle, and the velocity. So here's the vehicle again as it interfaces with the other components in the lab. So it gets the pose from the IPS, and it receives its commands from the high-level controller, and it sends the states back to the high-level controller. And now we need to worry about how can we compute this command, or how do we determine this command, which is basically what interests you most. So the high-level controller is, of course, in the planning sector here. So its responsibilities are decision-making, and also if you have a network scheme, then you need some sort of coordination between your high-level controllers. And these are the parts that make the high-level controller. Responsibilities are sending commands to the vehicles, and it executes your algorithm that you want to evaluate on a specific scenario. So in the CPM Lab, as I mentioned before, you can have your HLC in any programming language, as long as you have this interface to the DDS. So high-level controller gets pose and state from vehicle and IPS and sends the commands to the vehicle. So what's missing now is the scenario. How can you define scenarios to evaluate your high-level controller in the lab?
Just a quick question.
Oh, yes, please.
How is the middle-level controller implemented? So Baum said something about ROS2 in the beginning. I don't know if you're using that.
So we call the mid-level controller anything that the Raspberry Pi does. So I think are you talking about the middleware?
No, just how it's implemented on the Raspberry Pi. So is it just executable program written in C, or is there any kind of framework used to implement all these different modes also?
The mode or the software that's running on the Raspberry Pi is just written in C++. So you can find this also in this openly available software repository. If you're wondering how we implemented the path tracker, for example, or the trajectory follower. So this is custom implemented.
Okay, yes, it's just a direct implementation. I thought you had something like a framework to handle this.
No, so the framework we're using is just for the communication between the components. Yeah, so this is the DDS implementation, which is called RTI, RTI DDS Connect. Yeah.
Thanks. Yeah.
Okay, yeah. Okay, so scenario definition. How can we define scenarios? In a scenario, you would have, of course, the map that is used currently, and yeah, somehow you need to get to it. So you could have a scenario server where you can pull your scenario from, and this is yeah, we have this cooperation in the priority program, as already mentioned, and in this priority program, or part of this priority program is also a program called a common road. So this is a tool, what to say, common road, and it takes the idea of, or do you know the how neural networks really got boosted in development once there was a simple way to test for their performance, which was this, like you had a large set of images available, and then you could do classification tasks on these images, and then everybody could work with the same set of training data and the same set of evaluation data for the neural networks, and then you could get scores. How well did your network perform to classify these images? And Common Road takes this idea and transfers it to trajectory planning. So in trajectory planning, you usually have the same problem that everybody evaluates their trajectory planners on their own custom created scenarios with their own parameters of vehicle models and stuff like that. So it's really hard to compare trajectory planners. And so this is kind of a way to benchmark your trajectory planner. So it defines a scenario and it defines models and parameters for them, and then you can just see how did my planner perform compared to the other planner. And yeah, it has various components. For example, the streets are made up of lanelets. This is like a format which defines where are my left and right bounds and how are the street is split into several parts, and then how are they connected? Are they lying next to each other? Can I go from one street to the, or from one street part to the other? Stuff like that. And then you can have static and dynamic obstacles. And of course you can have, or you need to have like a certain objective that you want to reach with your trajectory planner. So you have initial state of your controlled vehicle, and you have a goal state that you want to reach. Okay, so these were all the components that we have in the lab.
Sorry, I have a question for this.
Yes, please.
Common road. So this is just for evaluating like motion planner of single vehicles, or like does it has other function as well?
Yeah, they also have planning problems for multiple vehicles, so it's not limited to one vehicle. But yeah, that's their main goal. But what we use it for is mainly because, twofold. For one, we can use the way they define scenarios. In order, like, so if you have a certain map that you want to use in our lab, then you can just use this format and then define your map in this format. And also second, this benchmarking is also done in simulation. So if we create this interface to this scenario definition, then you could also run any trajectory planner that you can test there. You can test it in experiment in our lab.
I see, thanks.
Yes, okay. Okay, yeah, so let's go on to the experimental concept. Yeah, the experimental concept has, I want to talk about three points here. So one is we have a hierarchical architecture. And the second is our components here either work in real time or they work, they don't worry about real time, but they just work as best as they can whenever they are triggered. And yeah, between the components that you have in this hierarchical structure, we need some kind of synchronization. So in order to have like deterministic experiments in order, so yeah, everybody is on the same page, roughly speaking. Yeah, the hierarchical structure in control is really common if you have planning and control, because usually the planning problem takes much longer than or takes really long. And if you want to control your actuators, it's usually better to have shorter control loops, to have more smooth actuation. And yeah, I will just go through the illustration here. So we have this the hierarchical structure here in three parts. Our high-level controller, as I said before, is separated from the vehicles due to the small size. And the high-level controller is just a normal PC, which is responsible for the trajectory planning. And then we send the trajectory to the vehicle, which it's received on the Raspberry Pi, which plays the role of the mid-level controller. So in the case of the trajectory following mode, it computes the control actions for the trajectory to follow this trajectory. And it also takes care of time synchronization. And it sends the control inputs to the Atmega microcontroller. Between these two, between the mid-level and the low-level controller, we have just like SPI communication. So they are really connected with wires, and they are running in real time, and sending back the estimated states to the development computer. The development computer is running in the triggered mode. So whenever it receives new information, it just starts to compute and does the best it can. And yeah, so the idea behind this that you just want to test your algorithm. You don't want to worry about all this synchronization stuff. And so if we provide you with the framework and if we tell you whenever you need to compute something, it's really easy to test your algorithms. And this trigger is also what I was indicating at the beginning when I talked about, why do we need this middleware? And one job of the middleware is to do the triggering of the high-level controller. So in this image, you can see the time progressing here to the right. then you have these lines indicate control loops or sampling times. And yeah, it's indicated here that the mid-level and lower-level controller, they run really fast. So in our lab, 20 milliseconds sampling time, and they are always exchanging data, sending control inputs, and reading measurement data. And whenever something new is available, the mid-level controller writes it to a topic which the middleware reads, and the middleware again takes care of time. So it's the middleware runs in real time and always watches when the set period is over. And once the period is over, it takes the newest measurement that is received up until then, and sends it to the high-level controller. And whenever the high-level controller receives this command, it starts to calculate or does its computations. And whenever it's ready, it sends the commands back to the vehicles. And yeah, as you can, or as in this example, the high-level controller finishes its computation. I'm not having this laser pointer, so this might be more helpful. The high-level controller finishes its computation in this in its sampling period. So everything's fine, but because there's delay in the network, so it needs to send the command as well. And then when it sends the command and when the vehicle receives it, it's a bit later than the high-level controller would expect it to be. And if you know, if you know about this delay, then maybe I should start over again. It's bad that you don't know when your data actually arrives. But if you can estimate an upper bound on this, then you can. We realized determinism in the lab by just allowing you to determine a timestamp at which this command should be valid. So if you know, okay, I need far too long to submit this data, so please just wait until this time or that time or whatever. And then the mid-level controller will see, okay, I have new data, but it's not valid yet. And I will just use it whenever I'm told to use it. And this way you can kind of negate this effect of varying communication delay and have repeatable, deterministic experiments. Yeah, that wraps up the part about the concept. Do you have a question about this experimental concept? I will go on with rapid functional prototyping. So the system we want to test in the lab consists of a plant, the vehicles, and your controller. And we have two, let's say, two operating modes, how we can do this. So first, what we will do later also is work in simulation. So we have the plant, which is the vehicle, and possibly the IPS, because you get measurement data from it as well. Both are simulated, and your controller will run on your own PC, so on a desktop PC. And apart from that, we have the real lab where we do the experiments. So there we have the real plant, the real vehicles, and we have the controllers, which also run on desktop PCs there. Since again we are using in both versions we use DDS as our means to transfer data. So it's also really easy to transfer your algorithm to the real system, because we just switch out the simulated vehicle with the real vehicle, and then you're good to go. And yeah, usually, well, a general naming convention of these testing, of these tests, of these experiments is in the loop testing, and there are many variants of it. So if you're developing algorithms or controllers or whatever, you can go on different levels of how close are you in your, or are you still in prototyping process, or how close are you on deploying it, like actually your code on the microcontroller that it will run on in the real system, or and in the real and using the real plant for it. So for example, if you have the plant, you can have maybe 3 different versions of how close are you to reality. So you can have a model of the plant running on a desktop PC or on real-time hardware, or you could have the real plant. And same goes for the controller. So you could have the controller written in as a model, for example, in the desktop PC, or as the real code that you're going to use on a desktop PC, or you could have it on specific evaluation hardware or on the real hardware that is going to run. And yeah, there are 3 possibilities for the plant, and I think 5 for the controller. So there's 15 combinations of that, and people try to find names for this, for all these combinations. So there's hardware in the loop, software in the loop, a model in the loop, and stuff like that. But we thought we'd make it easy and just say it's X in the loop. And if we want to communicate what do we actually mean, we just say, okay, I have this plant on this controller, and then nobody has to look up definitions for how to call this in the loop testing. Okay, so short note on software development processes. Now I have it. So you all probably know various models on how to develop software. So the waterfall model, or the V model, just to name the classics. And I find them really hard to implement or to really use. But I want to talk about extreme programming now, which is, for me, it's really natural and easy to use. So it has some aspects that I'm going to talk about. So what you're trying to do is you want to develop in small increments. You try to find what is most important first, and you try to implement that first. And it also has the paradigm of using unit tests. So ideally, you would write a test first for the code you are going to develop, and always have working code with this automated testing. And what perfectly fits into this course is that it's done, or it takes code review to an extreme by just doing pair programming. So you always have one person programs and the other one looks above the shoulder and checks what the other does. So you always have code review on the fly, so to say. And this is really easy for you to do if one shares the screen, and then you can work on something together and just using extreme programming. Yeah. So there's also no explicit design. Everything is just as a design documentation is all in the code. So it's also good for small projects, but if this course is a small project, so perfect. Yeah. Software design. Usually you design software so that it's easily maintainable and you have reusable parts of software, and yeah, it's clear, you can easily understand it, and there are design patterns to do this, the Gang of Four, for example. And yeah, I used MATLAB in my studies a lot, but it took me really long to find out that also MATLAB supports many functionality of this. For example, you can have, I didn't, for longer than I like to admit, I didn't know that MATLAB had classes, for example, and you can have structs in MATLAB or in functions. So a lot of stuff you can do also in MATLAB. Yeah, so if you didn't know about it, look it up. And yeah, and another idea to do is for implementing, or for software development, is to find subsystems of your software. And so a subsystem then can work standalone, have defined interfaces, and it consists again of closed components. So this is again, subsystems is also again for ease of maintenance and transparency, so you can easily understand what's going on, and you can switch out a subsystem if you don't, or if you have a better version, or if you have another version. Yeah, so as Manuel already realized, I invited you to a Git repo. Yeah, I would like to ask you to have your code always up to date in this Git repo. That makes it easy for us to run your code in the lab. So that's one benefit of it. We can just access your high-level controller then and run it. And of course, it's always a good idea to have your code versioned in some tool. So here are the bare minimum of Git commands. So probably you will be fine with those. If you have any questions about this, just ask me or ask your teammate. And you can find great documentation about Git online as well. I will not really go into the depth here. And I also have a small exercise on Git, I know, because our lab software this is an active development. So we're actively developing still the software in the lab. And of course, we have updates. So I'd ask you to, in the after this talk, just to go to the software folder in the dev folder where the repo lies, and then you don't really need to check out the master here, but I just thought I'd put it here for completion. So just pull the newest version, clean everything out, and build it again. And then you've seen also the building process. Once it will take a while in the virtual machine. So yeah, best do it before the break starts. And yeah, you'll have the newest version. Yeah, here I'll talk about how to start an experiment in the lab. I'm not sure. So videos and PowerPoint is always confusing for me. I think if I click, it starts. Yeah. Okay. Yeah. What you see here is in the middle is the driving area. So this is the lanelet representation of the map that was shown in the video from Bassam, if you remember from in the morning when the vehicles would drive to the intersection and around in the outer circle. And on the right, we have various tabs where you have a functionality of this GUI. So in order to start your script, which you want to start from MATLAB, I recommend you just delete the path to the high-level controller here. So we call this GUI the Lab Control Center. The Lab Control Center has the ability to start your high-level controller as well, but if you are debugging, it's easier if you just start it yourself. So first delete this script path, then you turn on the vehicles that you want to use. So just by clicking on the corresponding button, the simulation starts. And then in this parameters tab, you can change the period of the middleware that you want to use. So this will also set the time duration in which your high-level controller will be triggered. So whatever you set here, this will be the time that will pass until you get a new trigger signal. Anything up to 500 milliseconds should work here. So because the vehicles, if they don't get a new command in, I think one second, they will assume that the high-level controller is dead and they will just stop. Okay, yeah. So set the value that you want to work with here. For example, I set 250 here. And then you just hit deploy and you go to the timer tab. And now you see there was an obstacle simulation popping up. This is just again from the common road definition. And then you go to MATLAB, and in MATLAB, in case you don't know, you can activate pause on errors. So whenever your script encounters an error, MATLAB will keep all the workspace variables open for you, so you can look into all the variables that are what values they have at the moment. So it's really easy for debugging purposes. And then here just enter the ID of the vehicle that you want to control. For example, here it was vehicle 1. And then MATLAB, the high-level controller will start. It will set up the communication with the middleware. So and with the LCC. So first it sends a ready signal, says, hi, I'm good to go. And then it waits for you to start the experiment. And you do that by clicking start here. And in this example, the vehicle just tracks a circle. And when you're happy, just stop the experiment, reset the timer, and kill it. Yeah, and then you see any outputs we have via high-level controller here in MATLAB. Okay, so one thing I want to mention here, if you're running your code in the virtual machine, it could be that you are missing, that your high-level controller is missing deadlines here. So it's not fast enough to keep up with what it should be doing. But don't worry too much about it. You can, of course, work with the sample time, but also in the lab we have a much more powerful computer which works on which Ubuntu just runs natively. So yeah, don't worry too much about it. Okay. Yeah, that's all. Are there any questions?
Yeah, thank you, Patrick. So maybe the questions will come when you start your the lab in Ubuntu or in the virtual machine, wherever you are going to work in. So I have some comments also for the lab work.
Please.
Can I continue? Yes. Okay. Yeah, we have participants here coming from other backgrounds in aerial and underwater vehicles. And as you saw in the architecture Patrick showed, the coordination algorithms you can implement in the lab, you can take them and replace the model, and hopefully they will work. No, they will not work directly, but the lab is modular in its architecture. So we hope that you can transfer the algorithms you develop here to your applications and to your areas. So for the lab work, we divided you into 7 teams. All teams have 2 members, but team 7 has 3 members. So I tried to give my best in assigning you to teams. So I used the form feedback from you about your background, and the main topics I considered are programming and control. Please check with your teammate how is your control and programming background. In each team, at least one of you should be strong at programming or at control, at least. So in best case, you 2 are strong in control and programming. But if this is not the case, please tell me. We can change teams. There is no problem in changing teams. And today is the getting into the lab work. So you can use also today to see if you can work well with your teammate. If not, it's no problem. We can change around the teams, and there are also other options. I considered also that diversity, so that, for example, you are from different languages or from different countries. So just to mix things up, to have more fun here through the interaction. And for teamwork, we defined breakout sessions in Zoom. Patrick, I cannot see the breakout sessions in my Zoom.
I can see them. Maybe I have to begin then. Let me try.
Now, okay, you have to begin them, right?
Okay.
So if you click on breakout session now, it's next to the action. You will see team 1 to 7. So you can just click for teamwork. The Zoom meeting here will be open the whole time. Just go to the main room. This is the main room. And from here, from the main room, you can go to the teams, to the breakout sessions. You will find your teammate there. Work on the lab. And if you have questions, Patrick, and maybe I will stay also there, you can come and join us here and ask your questions. You can also visit other teams in the breakout sessions. If you would like to discuss things with other teams, you can go to their breakout sessions. So for communication, you can use the chat in Zoom. If you would like, you can put also your whatever you would like to use for communication. You can start WhatsApp groups or whatever. So it's completely up to you. So I think that's all. Let me check. Yeah, I think everything is said. So we have still in this session time for teamwork. So I suggest that you now, okay, before going to the teamwork, a question to Patrick. Exercise sheet number 1, is it online?
It will be in 1 minute.
Okay.
But yeah, we can, or I suggest to go through it really.
Yes,
quick.
it's a good idea. Yeah, before going into the teams, Patrick will introduce the exercise sheet number 1. So just give him a minute to prepare his screen.
Yeah, so excuse me that I'm not looking into the right screen now, but yeah, so this is the first exercise sheet. So starts with a link to the documentation of the lab. So if you are wondering about if you're looking for information, you can always check out this documentation. Of course, as Bassam said, you can also just go back to the main room and ask me if you're stuck or if you're not. Yeah, if I have a specific question. The first exercise will be about how to set up the machine. So you should be able to skip the part A. Then the second part is just about setting up the repository. Exercise 2 will be about the different vehicle modes and the communication with via DDS. And exercise 3 is about a position control of a vehicle in path tracking mode. So you will, one part of the exercise is to create a longitudinal model of the system and then use this state space model to implement a model predictive controller to follow like a reference position along the path. So that's the first.
Okay. Now the exercise sheet is in share out, right?
I hope so, yeah.
Okay. Let me check it. Share out. Yeah, one introduction, right?
Mm-hmm.
So you should find it in the share out. Again, a hint on slide number 36 of the presentation of Patrick. There is a Git exercise. So I would suggest that you start with this exercise before starting with exercise sheet number 1. Yeah, because you update your repository there. Yeah, I would suggest that you now go to the breakout sessions to your teammates, and we will meet here again 3:30 to.
I just have a question: how to join the teams?
To the team in Zoom. In the bottom, you have different buttons, and one of them is breakout session. It's like the symbol of Windows with four rectangles. Do you see it?
No.
No.
Okay. Patrick.
Does nobody see it?
I don't think you have created the breakout room yet.
Me neither.
Okay, then the option isn't set. So it is just for me now, or?
Yeah, so I can put you into breakout sessions, but so are you all using the Zoom client, or are you joined through browser?
I'm using the client, and I still can't see.
Okay. Yeah, maybe I'll just do this manually now, and I will see what the problem is here.
So we will see you again in 15 minutes here. Maybe use the time to get to know your teammate and check if you can work together. Start exercise sheet number 1, see what you can do in 15 minutes, and yeah.